What we're going to do now is use some of these basic concepts to help us solve a circuits problem. And the technique we're going to use is called circuit reduction. It involves replacing networks of resistors with their equivalent resistances. In other words, we're going to make like several resistors at a time and replace them with just one that has the same resistance. And that will allow us to do some of these analyses. Now, I would say if you have a choice between using this method and using Kirchhoff's laws, which we're going to cover next, this method is actually quite a bit easier. So try to avoid using Kirchhoff's rules, often called Kirchhoff's laws, either one. But we're going to use circuit reduction whenever possible. So what does that mean? Well, we got to identify which of these resistors are in series and which are in parallel with each other so we can replace them with their equivalent resistors. So what I've got here is a seemingly complicated circuit with I've got a 12-volt battery here, right there, 12-volt battery, or power supply, and it's feeding or providing EMF for this entire circuit right here. Now, I want to start replacing these resistors with their equivalents, but I got to figure out which are in series and which are in parallel. Let's start with this 1 ohm resistor and this 10 ohm resistor. Are those in series or parallel? Well, the answer is neither. They are not in series nor are they in parallel. They're not in series because every electron that goes in here does not have to go through that 10 ohm, and there's a split right there. So it does not have to go through that 10 ohm. They are not in series. Are they in parallel? No, because it doesn't split right before the two. So those are not in series or parallel. That's not going to help me. Let's try the 10 ohm and the 25 ohm. Are those in series or are those in parallel? Well, you'll notice that the current splits, coming out of the positive end here, current splits right there, and then it joins back up together, so current goes this way and this way. It joins back up together there, so it comes back together right after those two. In fact, those are in parallel. So I'm going to find an equivalent resistance that's equal to these two. I'm going to replace that with the equivalent resistance of those two. So I'm going to redraw it like this. And it's important to redraw every single time because this is how you do it right. Make sure you redraw that. What I've got is I've still got my 12-volt battery, 12 volts. By the way, the long end means positive. I've got my 1 ohm resistor right here, 1 ohm still there. But I need to figure out this equivalent resistor right there and our equivalent for the 10 ohm and the 25 ohm. So I'm going to call that our equivalent for 10 and 25. It's somewhat of a complicated notation there, but that's what I'm trying to get. And then I'll have my 2 ohm resistor. Hey, that's not going to be so bad. Once I find this, I'm just going to figure this out right there, and then I'm going to have a really easy time analyzing this. So let's go ahead and figure out what that equivalent resistance is. Okay, so it's a 10 and a 25 in parallel. So our equivalent for the 10 and the 25 is equal to 1 over 10 ohms plus 1 over 25 ohms. The common denominator of that is 250, so that's going to equal, actually it'll be 50 is the common denominator. So that's going to be 1 over, it's 5 over 50 ohms, plus 2 over 50 ohms. And that gives me, this is 7 over 50, 50 over 7 is the final result. And that's, let's go ahead and figure out what that is decimally. 50 divided by 7 gives us 7.14 ohms. So this one is equal to 7.14 ohms. And to make sure that's right, conceptually, it must be less than either of these individual ones, and it is. So it looks like we've done that correctly. So we've got that. Now we can find the current through every single one. Why? Because now we've replaced this right here with its equivalent one single resistor right there, and now these are in series. So we know the current has to be the same throughout all of them. What I can do is one more step here. I can replace all these three in series, and this step you actually can skip if you want, with its series equivalent. I've got a 1, a 2, and a 7.14. What's the equivalent of that? Well, that is just adding them all up. So our equivalent in series is just R1 plus R2 plus R3. So I'm going to really just replace this. Here's my 12 volt again, 12 volt battery. And all I've got in here, just adding all those up, is simply 1 plus 7.14 plus 2. I'm getting 10.14 ohms. And now it's easy to figure out the current total is equal to 12 volts divided by 10.14 ohms. And again, I'm just doing V total over R total is what I'm doing there. Delta V total over R total is what I'm calculating. And when we do that, 12 divided by 10.14 is approximately 1.2. It's a little bit less than that. Let's go ahead and figure out what that is. 12 divided by 10.14. And that's giving me about 1.2 amps. We can round. We'll call it 1.2. 1.18 amperes. This is I total. This is the current leaving this and actually entering this, but it's also the current going through this equivalent resistor. So now, what is the current through each one of our resistors? Let's look at the original one again and figure this out. The current through our 1 ohm resistor, well, that's the same as the current leaving the battery. So the current through the 1 ohm resistor, which I will call I through the 1 ohm, is equal to 1.18 amps. The other easy one is going to be the current through which one of these? Well, that's going to be the current through this one, because that's also going to be the total current. Current through the 2 ohm is also 1.18 amps. Now, what's tougher though is the current through each one of these. It's not 1.18 through each one of those. The total, if you add up the current through these, it'll be 1.18 amps, but it's not the same as saying it's 1.18 amps through that and 1.18 amps through the 10 ohm and the 25 ohm. That's just not true. How do we get the current through each one of these? Well, it's really not that bad. What we do is we take that equivalent resistance and we figure out what the delta V is from that. So let's figure out the delta V across the equivalent, R equivalent, which is made up of the 10 and the 25 ohm. Let's figure out what that is. And all we got to do is, we know its equivalent resistance, that's not it. The equivalent resistance of those two in parallel, we already have. It is 7.14 ohms. This is 7.14 ohms. So what we get is delta V is going across the 10 and 25 equivalent is going to be the I through the 10 and 25 equivalent over, times the R of the 10 and 25 equivalent. So that is, what is the total current going through both of these? Or really, you say, what's the current going through there? That one, if you just look at it this way, that is the total current going through there. So that's going to be, through that equivalent resistor, it is 1.18 amps. And the equivalent resistance is 7.14 ohms. When we do that calculation, we get 1.18 times 7.14. And that gives us a delta V, the voltage drop, delta V, is equal to 8.43. 8.43 volts. 8.43 volts. Now, Now we can figure out what the current through each one is, because this is the delta V across the combination of the 10 and the 25. So that's the delta V across this combination. They're in parallel, so the delta V from there to there is the same. It's the same across the 25 ohm, it's the same across the 10 ohm. So now I can figure out exactly what I want to, which is let's go over right over here. The current through the 10 ohm is going to be the delta V across the 10 ohm divided by the R of the 10 ohm. And now I'm looking at them again like this, back to the regular. I'm going back to this one right here, and you have to do that. That's why you have to redraw all of them and keep your original one, because I've got to go back to that. That is going to be the delta V across it, as we just found out, is 8.43 volts. And you divide that by the resistance of the 10 ohm. Now I'm back to looking at it as just the 10 ohm. And that's going to be very simply 0.843 amperes. 0.843 amperes. Now you can figure out what that the current through the 25 ohm is a couple of different ways. It's like a crossword puzzle, because we now can figure it out a couple of different ways. Let's figure it out the same way we did this last one. The delta V across the 25 ohm over the R of the 25 ohm. That's going to be, delta V is the same, 8.43 volts. Notice the 10 and the 25. Notice the 10 and the 25 are in parallel. The voltage difference will be the same. So it's going to be, but it's same voltage difference across a 25 ohm. And that is going to be equal to, let's go ahead and do the calculation, 8.43 divided by 25. And that gives us 0.34. 0.34. Now, you may notice, this is amperes, what do these two have to add up to? This one right here, this one, and this one, they have to add up to, by looking at our original diagram, the currents through there have to add up to the total current. This plus that has to add up to our total going through all these. Let's just see if they do. Our total current is 1.18. What is 0.843 plus 0.34? It is approximately 1.18. Again, it works. So the sum of those two, and this is a great way to check, you can just make sure that everything is consistent. Notice that when you add these two, they add up to 1.18 amps, our total current. Now we rounded here and there, so we might have a little bit rounding error, but overall it did work.